while we haven't exhausted everything we know about or need to know about an AP, we're going to move on and introduce the concept of a GP. And it's very important to get a full understanding of the difference between an AP and a GP. And that's why we're introducing the GPs, even without having done everything that we need to do look at for an AP. So what is it that makes a GP different, which is what you have to be able, you have to know and be able to identify a sequence being either an AP or a GP. Well, with a GP, you won't have a common difference. So that's pretty straightforward. But remembering that not every sequence is an AP or a GP. There are other types. You could be given a situation where it was neither. So let's focus now on what does make a sequence a GP. So what we'll be doing is we'll be looking at the ratio of terms. So ratio, I think ratio is best understood as a fraction. So we know that our terms, all the notation is still the same. Our terms are term 1, term 2, term 3, etc. To think about the ratio of successive terms, that's 1 followed by another one, the ratio would be term 2 over term 1. That's the ratio of successive terms. Like I said, it's best to understand ratio as a fraction here. And the next ratio would be term 3 on term 2. So what we know about these ratios is that they are always equal. So we could have is equal to Tn over T, the one before it, n minus 1. Now, that is what you will use to identify a GP. Once we've got that, we call this common ratio, we use the letter lowercase r. A is still the first term, T1, A. N is the number of terms. Tn is what it represented previously, the nth term. But obviously now we're going to talk about the nth term of a geometric progression or a geometric sequence. You can see here if we have the terms 2, 6, 18, 54, very clearly there's no common difference. However, if we think about the ratio 6 over 2, 18 over 6, 54 over 18, you can see that they are all equal, and that is what's required to show that you've got a GP. Again, it is a situation of recursive form because we can express Tn over Tn minus 1 equaling r, or we could write Tn is equal to r times Tn minus 1. So we're expressing a term in with respect to the term before it. Okay, that then means that all terms, we can have a general form for a term. We know we start with A. We're going to multiply it by R to create our second term. Multiply that by another R, and so on. And so we've got the formula that Tn is equal to A times R to the n minus 1. So that would be T1, and there's no R, it's R to the 0. This would be T2, and it's R to the 1. This would be T3, and it's R to the 2. So yes, you can see that the power of the R is 1 less than the number of the term. R can be a negative. R can be a negative. Don't confuse that with N, but R can be a negative. And you when you see a sequence written with alternating positive and negative terms, alternating, then it's most likely a GP where R is negative. And if you can see that and identify that in the sequence, it'll make it easy for you to identify that the sequence is a GP. So really, two main differences between an AP and a GP, and that is in an AP you have a common difference, in a GP you have a common ratio. And obviously then that leads on to your having different ways to define your terms. Having a look at this first example, you can see we've got the sequence 2, -6, 18, -4. So here's an example of this alternating positive and negative terms. We can see that clearly it's not an AP, and if we put -6 on 2, you get -3. 18 on -6, -3. So to show that it is a GP, we'll do -6 on 2 is equal to 18 on -6 is equal to -54 on 18, which is -3. Therefore, and don't forget it says find the value of R. R is equal to -3. And you can imagine, start with 2, multiply it by -3. Of course, you'll get -6. But multiply that by -3, you get +18. Example 2, complete the formula for finding the nth term of the GP, where we have, well, you can see A is equal to 5, and R, well, we don't have alternating signs, 10 on 5, 2, 20 on 10, 2, so R is equal to 2, and then we've got to determine if 320 is a term. So, by definition, the nth term is A times R to the n minus 1. So, in our example, we'll have A is 5 times R is 2 to the n minus 1. Now, we want to know whether 5 times 2 to the n minus 1 is equal to 320. Divide both sides by 5, 2 to the n minus 1 is 64. Now, we've got, what have we got? We've got an equation to solve. N is in the power. Now, we've got a few ways we could do this. We could look at taking the log of 64 to base 2, equaling n minus 1. Log of 64 to base 2, we then have to use the change of base formula. Alternatively, we could say, and this is where, if you recognise 64, that 64 can be written as 2 to a power, it really helps. So hopefully we know that 64 is 2 to the power 6. Now, we've set this equation up, same base, which means the powers must be equal, n minus 1 is 6. So in this case, n is equal to 7, which is a whole number, which is what we need to happen if a number is going to be a term. We have to have a whole number for n. In this next example, you can see that it says the first term of a GP is 48. When I read that much, I note that down and pull it out of the words and make it obvious and sitting out here looking more mathematical than a sentence. The seventh term is 7, or T7 equals 7 is how I translate those words and make it look more mathematical. It says find the common ratio, so I'm finding R, and write out the first 5 terms. There'll be term 1, term 2, term 3, term 4, term 5, And always note, if they give you a hint, which they don't very often, there are two possible sequences. So where would we start? We know that A is 448 and T7 is 7. Basically, that's all we know. Well, there is something else we know. We know that the nth term can be written as A times R to the n minus 1. So the nth term could be written as 448 R to the n minus 1. Now, we've got two unknowns, which is a problem for us. However, we've got a particular term, and that's now what we'll use. We know that when n is 7, the term is 7. So this term, 7, is when n is 7 and n minus 1 is 6. So you can see there I've produced an equation now with one unknown. One equation, one unknown, we can solve. So we're going to divide both sides by 448 and get r to the 6th. I don't know, maybe I'll go to my calculator. And luckily I did, because 7 on 448 is 1 on 64. And to be honest, I looked at that 7 and 448 and thought, nothing about those numbers is familiar to me. And, really, while sometimes the numbers will turn out to be absolutely horrible, in a lot of cases they do choose particular numbers so that the working is pretty nice. And you can see now it is 1 on 64, 64 to the minus 1 is r to the 6. What is another way to write 64? 64 could be written as... Oh, actually, I've had a rethink about that, and as you can see, I've taken the negative power out. I don't want the negative power. 1 on 64 is, well, I know the connection between 2 and 64. We needed that for the previous question. 2 to the power 64, 2 to the power 6 gives you 64, which is really convenient. I've now got the same, I can equate the bases, and I've got the same index, and I can say that r is equal to. Now, I guess really this could have been plus or minus 2. So I've got plus or minus a half. And then I'm going to list out my first 5 terms. I know the first term is 448. Using term 2 would be a times r to the 1. You can see, I'll drag the calculator in, that term 2 would be 224. And you can just keep changing your power there without rewriting the whole sum. Or you can just keep halving the numbers, probably easier. 112. What's this? 66. How many have I got? And 33. 1, 2, 3, 4, 5. I'll leave the rest and do them in class with you.